All right, this is the section 3.4 definition of a function in class notes. Objectives for this video are going to be to learn the definition of a function, domain, and range, how to evaluate functions, finding domain and range from a graph, and domain only from an equation, because it's not easy to find the range that way. Determine if a function is increasing, decreasing, or constant, evaluate the difference quotient, and then write the equation of a linear function. So a function f from a set D to a set E is a correspondence that assigns to each element x of D exactly one element y of E. So that's the formal definition of a function. A lot of times people have a hard time mapping what that actually means. So I'm going to draw a little picture of kind of the difference of what would be a function, what wouldn't be a function. So if you think of having a set, which that's too thick, hang on just a second. Let's erase that and make it smaller. So if we have a set D and a set E, and we're trying to map between one to the other, the idea here is that to be a function, an element in D has to map to an element in E, and what can't happen, so this is okay. What cannot happen to be a function is that you can't have an element in D mapping to two separate elements in E. Okay? So we can't have the same element going to two separate ones. Now, it is okay to have two separate elements in D go to the same y value. The key here is that each x has to only be used once when you map through. So that's really it. So each x must be unique. That's how I like to think of it. So if we're looking at that, that's the definition of a function. Now, one way to tell graphically if you have a function is to do something called the vertical line test, where you draw vertical lines across your entire graph, and each vertical line can only cross your graph once per vertical line, because that's really testing that each x is unique. All right, so the first example here is we're going to do some evaluations. We're going to do f of a. I'm going to write all of these down here so we can see it clearer. And I don't know why this is defaulting to a larger ink. Hang on just a second. I'd like it to default smaller, but it doesn't want to listen. All right, so we're going to be doing f of a, f of negative a, negative f of a. I'm looking at my list up here in the directions. We're going to do f of a plus h. We're going to do f of a plus f of h. And then we're going to do f of a plus h minus f of a all over h. And this actually has a special name later on. We're going to call this the difference quotient. Remember, that was in our objectives. But this is really just pieces of what we've already done up here. So when you're doing a function evaluation, you're taking the f of the variable, which usually is f of x, and you're going to be substituting things in for x in your function, your equation that's on this part, the right side. So for this first one, I'm plugging in a wherever there used to be an x. So that would be 3 minus a squared, which there's nothing really to square there since we don't know what a is. So it's just going to be 3 minus a squared. For the second one, I'm plugging in a negative a. So this is where we actually do have something to square. If you square a negative 1, it actually comes out positive, but because there's still a minus in front of there, it's still going to be 3 minus a squared. But I did square the negative a. This is a negative 1 times my entire function evaluated at a. So we take our answer from the first part, and we're going to be multiplying it by negative 1. So that's going to be negative 3 plus a squared when we distribute that negative 1. For this one, this is a binomial. This binomial is going to replace the letter x. This is not f of a and then plus an h at the end. This is an entire binomial going in for your x term. So this will be 3 minus a plus h squared. So we're going to have to FOIL out that a plus h and then distribute that negative sign. So that's going to be 3 minus, and then we'll have a squared plus would be 2 ah's and then plus h squared, and then we distribute our negative sign. So 3 minus a squared minus 2ah minus h squared. So it's really important when you plug a binomial in where you once had a singular variable that you go through the whole simplifying process. This is different. This is f of a plus f of h. So it's two separate evaluations. So one evaluation is 3 minus a squared, plus the second evaluation is 3 minus h squared. They're completely separate from each other. So this would be 3 plus 3, so we can at least add those two together. So that's going to be 6. Oops. Sorry, anytime I reset it, it wants to change the thickness back to full 1. So let me make that a half. So this would be 6 minus a squared minus h squared, because the a squared and the h squared are not like terms, have different variables, so we cannot add them together. Okay, for this last one, you're just taking two of your answers from up above, and they're going to be placed into here. So notice we have this, which was this answer. So that's going to go in on top. And then we also had negative f of a, which was this one, which is this. And that's going to go in for this. And then all of that is being put over h at the bottom. So we're going to work that piece out. So this is going to be 3 minus a squared minus 2ah minus h squared, that was all of the yellow, minus 3 plus a squared all over h. Now, when you've done the difference quotient, which is what this is going to end up being called at the end, because we're going to define it and actually tell you what it's doing in just a little bit, this is going to happen. You're going to have some things that cancel out. So the 3 and the negative 3 are gone, the negative a squared and the positive a squared are gone. That's negative 2ah minus h squared all over h. And notice that everything has an h on top, so we can actually reduce this. So minus 2a minus h is what it would reduce to. So we're going to do the same set of evaluations for part B. So we're going to do an f of a, an f of negative a negative f of a plus h, probably going to need a little more room for those this time. Then we'll have f of a plus f of h, two separate evaluations, and then finally the difference quotient. Okay, so let's go through. This time there's two different x's in my function, so I have to plug in the a for both x's. Sorry, let me put the square on the outside. Keep consistent. So 2a squared plus 3 times a minus 7. When you square a, it's still going to be a, so it's going to be 2a squared plus 3a minus 7. So there's not really much to do for that first one, just plug and chug. For the second one, though, we're going to be plugging in a negative a. And sometimes that will change the way the equation looks. So when you square a negative, it's going to come out positive still, so that's still going to be 2a squared. But a 3 times a negative a will be a negative 3a minus 7. So notice this is no longer the same as the original because the 3a changed signs. For the third one, we're doing negative 1 times the function evaluated at a, which was our answer from the first part. That's negative 2a squared minus 3a plus 7. So all the signs have been swapped. The binomial is going to be a little more work here because there's two x's to plug in for. So we have to show it twice. Both of those parts are going to get an a plus h. So this would be 2 times a plus h squared plus 3 times a plus h minus 7. Every time you FOIL out a plus h times a plus h, it always ends up being the same trinomial. It's a squared plus 2ah's plus h squared. You'll get that pattern down just the more you do it. Then we'll get 3a plus 3h minus 7. Last thing to do here is to distribute that 2. So it's 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 7. Notice it's very long and it doesn't have any like terms, so we can't even combine any of the terms together. For this last one, remember this is just two separate evaluations. F of a is 2a squared plus 3a minus 7 plus f of h would be 2h squared plus 3h minus 7. If we add those together, that is 2a squared plus 3a plus 2h squared plus 3h, and we can combine the 7s, so negative 14. Okay, so let me highlight again. Remember that f of a plus h is this answer right here. Negative f of a, including the negative sign, so we've already taken care of that, is this answer here. So we are putting those in, remember, in terms of the numerator of our problem for our difference quotient piece. And it is all still over h. So the answer for the first part was 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 7. For the negative f of a part, the answer was negative 2a squared minus 3a plus 7, all over h. 2a squared has opposite, 3a has an opposite, and negative 7 has an opposite. So I'm left with 4ah plus 2h squared plus 3h all over h. And again, if we've done this correctly, every term on top has an h. So if you divide each one of them by h, you're left with a 4a plus a 2h plus a 3. So that's just dividing it out. Each one of them loses an h. Okay, so that's evaluating functions, and that's evaluating functions without just plugging directly numbers in. It's obviously easier if you're just doing like f of 2 because you're just plugging in a 2 for all your x's and you're working it out using order of operations. It's the plugging in with variables that's always a little trickier, so that's why we covered that. Now, if you're looking for domain and range, domain has to do with what x values are allowed in your function. And what we mean by that is, are you allowed to plug them in means, can you plug them in and get a real number answer? So if you ever make something where you divide by 0, that wouldn't work. That couldn't be in your domain. If you ever have a square root and you plug something in and you get a negative underneath it, that would be an imaginary answer. So that also would not be in our domain. So the biggest two functions that have issues that we've learned about so far in terms of domain are square root functions and rational functions. So here's a picture of a square root function. This is the square root of x minus 1. So notice it's got a little bit of a shift to it. It's not centered at 0 anymore. So this guy right here, it looks like you can't plug in like 0 because 0 minus 1 would be negative 1. That would make a negative number under my square root. That would be imaginary. So the way we find our domain when we're dealing with a square root function is you take the part underneath the radical and you want to make sure that it never goes negative. So to make sure it's never negative, you say it has to be greater than or equal to 0. So that's why the domain here is anything bigger than or equal to 1. And notice they've written it in interval notation. I could tell that from the picture though. If I just said, where do I have x values? That means where do I have blue graph? I have blue graph everywhere from positive 1 on the x-axis to positive infinity. There's no blue graph below that. And if I'm doing range, again from the picture, I can tell it as well. There's no blue graph below 0, but there is blue graph above 0. And this would keep growing even though it's going to take it a long time. It would eventually grow very large. Let me erase some of that. There we go. So this right here is, let me cover that in. So from 0 to infinity, I have graph. So my graph is completely above the x-axis. So that's my range. For my domain, my graph is completely to the right of positive 1. So that's what we mean by telling domain and range from the graph. You can look at the visuals. So we're going to do that for the next two problems. We're going to determine the domain and range of the function shown below. Then we're going to do two evaluation readings off the graph. F of 1, we're going to find that, and all values of x such that f of x equals 1. So we'll discuss what that means after we do the domain and range. So I'm going to use red for the domain markings, and we'll do blue for the range. So your domain on this first graph is, when do I start having graph? I have no graph above and below anywhere until I get to -4. So notice every value between -4, even -2, even though there's a split here, -2 is on the graph. It has a point. So every x value between -4 all the way up to right here at +1, I can pinpoint a specific piece of this graph connected to each of those x values, even the decimals. So that makes my domain for this graph -4 to +1 on the x-axis, because remember, domain is x-axis. For my range, I need to look up and down on the y-axis. So the lowest the graph can ever get is -4. And then I have graph, graph, graph. I have graph to the left and right, all the way up to almost graph here. I'm actually missing graph because -1 is not included here, okay, on our range. It's this open circle. Now, if there was another point somewhere on that same horizontal line that was closed, I could say -1 is included. But then next, notice there's no graph on this y-axis between -1 and 1. There's nothing to the right or the left. My graph doesn't start back until +1. And then I have graph all the way up to +3. Hang on just a second. Okay, for the range, it goes up to +3. So we're looking at two different ranges. So anytime you have two different pieces, we string those together, remember, with a union. So we're going to write the range as, this would be -4 because that's included, up to -1, which is not included because it's an open circle, unioned with, and 1 and 3 are both included. So all y values between 1 and 3. So that's my domain and range. So let's go ahead and do the same thing over here on part B, and then we'll come back and answer the other portion of this question. So it looks like our x's start at about -5, and we have every x value above or below, there's always a point, all the way up to +7. So my domain on this one would be from -5 to 7 inclusive. And the range here, the lowest my y value gets is at -1, and the highest it gets is +2. And again, I can find a point everywhere in between. If I go from left to right, there's always a point somewhere. So that would be from -1 to +2. Okay, so the second part of this problem was asking you to find f of 1, and what is that related to on the graph? So we'll want to do that for both of these. And then the second question of that was find all x's such that f of x equals 1. So I'll just rewrite that here. So let's just explore what this means. When you're doing function notation, f of x equals y. So the part that's in here is the x coordinate, and the answer on the other side is the y coordinate. So this says, if my x is 1, what is my y? That's what this first question says. Well, if I find 1 on the x-axis and find the point, -4 on the first graph is the ordered pair here. It's +1, -4. On this other one over here, if I find 1, I find that the y value is -1. So you're just asking the question, if this is x, what is y? The reason that's always just a single answer is because, remember, each x can only be used once to be a function. So the second question is saying find all the x's such that f of x equals 1. This is saying this is my y. So you're looking for ordered pairs where you have an x, comma 1. Well, that may be a single or it may be more than one. Just depends on that one, if there, because remember, you only have to pass a vertical line test to be a function. When you say a y is 1, you're looking at actually the horizontal line through 1. So this one only touches at this specific point on the graph. So this would say the x needed to be -2, because that's this ordered pair here, -2, +1. When I do that on this other one, though, you'll notice, I'm trying not to write through my actual points, it actually crosses my graph 4 separate times. So this one, there's 4 separate answers. The x's that all had a y value of 1 are -3, -1, +3, and 5. So that's why there's more than one answer, is because that's not violating the rules of being a function. It's just saying that there are all of these unique x's went to that same specific y value. Okay, the next topic is we've done domain and range from a graph. Now what do we want to do is find the domain just from an equation. And again, this is going to have to do with what type of equation you're given. So I'm going to write a little summary over here. So these are types of functions that we know of so far. And their implied domains. Okay, so the first type of function we ever discovered in this class was just polynomials. So that's just things like quadratics, linear equations. These have a domain that is understood to be negative infinity to infinity. You can plug any number on the number line into a polynomial and get a real number back. So there's no restrictions on polynomials. There's also no restrictions on absolute value functions, things that have an absolute value sign. The next type of functions we kind of talked about, even though we were just looking at them as equations, were rationals. So things where you have an x in your denominator. That's what makes something rational. This would be all reals, so negative infinity to infinity, except undefined values. So anything that makes me divide by 0, that's essentially what we're throwing out. And then the fourth type breaks into 2 cases. So I'm going to call it the odd root radicals and the even root radicals. That's the difference between cubed roots and square roots. So if you're an odd root radical, you don't have any issues. You can have a negative underneath a cubed root. It's just going to have a negative answer. But you cannot have a negative underneath a square root. So if you have square root of x, remember we said a minute ago, we have to make sure that stays greater than or equal to 0. So whatever's under your square root or your even root, we have to make sure it stays positive or 0. So that comes to our first case right here. This is an even root radical because it's a square root. So to find the domain, we say the inside of this has to stay greater than or equal to 0. So we're going to try to solve this. I'm going to subtract the 8 over, divide by -3. And remember, when you divide by a negative in an inequality, it flips the direction. So this says we can plug in any number as long as it's less than or equal to 8/3. And this makes sense to me because if you plug in, say, -2 here, a -3 times a -2 is a +6. So it's going to end up being positive overall. So this would be in interval notation because that's normally how we will write it, negative infinity up to 8/3 with a bracket. So that would be the domain for this first one. Now I'm going to come back to B in just a minute because it's a little more complicated, and I'm going to do C next because this is just a rational. So when you have a rational function, the first thing is you're going to try to factor that denominator. So let me make that a little thinner. So 6x squared plus 13x minus 5. This is going to be the AC method, so that would be -30. Factors of 30 are 1 and 30, 2 and 15, 3 and 10, 5 and 6. Be careful here. Everyone wants to pick 3 and 10, but that would be incorrect because, yes, that adds to 13, but this has to multiply to -30. That means you have a positive times a negative. You're going to have to use -2 and 15. So sometimes you're not trying to really add to the number. You're really subtracting because you have opposite signs. So just be aware of that as a big thing to look out for in factoring. So I'm going to put these 2 in for my middle term on that trinomial, and now I can factor by grouping. So I can pull a 2x out, that would be 3x minus 1. Pull a 5 out, that's also going to be 3x minus 1. So we have 3x minus 1 and 2x plus 5. So that's going to go up here as my denominator. Now, when you're talking about domain and a rational function, these cannot equal 0. We don't want them to equal 0. So to figure out what values to throw out, you actually set them equal to 0 to see what it would be. So 1/3 needs to be thrown out. This is -5, so that's going to be -5/2. So we're going to say that this is all reals except x equals -5/2 and 1/3. Now, if we want to write that in interval notation, that would be -infinity to -5/2. Use a parentheses because we don't want to include it. Then we'd go from the smaller number to the larger number because we want to shade everything in between the two numbers. Union with the bigger number to positive infinity. So depending how they want it written, they may just want you to write x cannot equal two things, or it may want interval notation. Okay, so I'm going to go back to B for a second because it is also an even root radical, but it's a little more complicated than just the one we did above. When you go to set this one greater than or equal to 0, it is quadratic. This gets into what we talk about in section 2.7. Anytime you have a quadratic or higher in an inequality, it's not so simple to solve the interval notation here, because both of these multiplied together will determine if this is greater than 0 or not. So what we learn in that section, which we're going to be doing on Tuesday together, is that you have to find the values from least to greatest that make those equal 0 and put them on a number line. So -5 makes this first one 0, 5 makes the second one 0. And we're going to test everything by using just one number from each interval. So we're going to have a test value. So -6, 0 is between them, +6 is bigger. You would plug that into your two factors. So this is my test value. This is what I'm going to test them into. And I hope that it comes out greater than or equal to 0. So kind of writing our inequality vertically. We plug this in, this would be -1, so I'm just going to put a negative. This would be -11. A negative times a negative, because we're multiplying here, is a positive. 0 plus 5 is a positive. 0 minus 5 is a negative. Multiply those together, that is a negative overall. So we don't even care what the number is. We just care if the number is positive or negative. 6 plus 5 is 11. 6 minus 5 is 1. So those are both positive. Multiply them together, it is positive. Since I want greater than or equal to 0, I'm going to go with the positive cases. This directly relates to intervals up here above my number line that I've drawn. This is everything from -infinity up to -5 and including it since we have the equal to. And this is from 5 to infinity, whereas this would be -5 to 5. So the two true regions in my domain are -infinity to -5 bracket, union with 5 to infinity. If you actually type this into Desmos, which is a graphing tool you can use, it's a free graphing tool if you ever want to check something. Obviously, you still have to show your own work, but if you type that into Desmos as square root of x squared minus 25, you'll see the graph only exists to the left of -5 and to the right of 5. There is no graph in between. All right, we have, I believe, two more of the domain ones. So if we look at this next one, this has two things. This is kind of a hybrid problem. It has a square root on top and it has the factoring in the bottom. So it has x's in the denominator. So what I do first is I usually focus on the square root, since I know that part will be restricting my domain already. So 4x is greater than or equal to 3. X is greater than or equal to 3/4. So right away, I know I can never use a number less than 3/4. So my domain has to start to the right of 3/4 because I'm greater than. I'm also not supposed to use any values that make me divide by 0. So I'm supposed to throw out -2 and +2. But -2, if you look at this on a number line, and then we have 3/4, and that part we're shading, and then we're supposed to throw out 2. -2 has already been thrown out. We just need to throw out +2. So I'm going to shade from 3/4 to 2, and then union that with the rest of the shading to infinity. So 2 to infinity. So when you're doing these hybrid ones, sometimes one of your denominator values may already get thrown out just by looking at the square root portion, because we knew that the square root said I have to be greater than 3/4, and -2 is already smaller than that, so it was already thrown out. The only difference between D and E is that my square root is in the denominator. That changes one little piece. Everything else is done pretty much the same way. If this is in a denominator, the only change is that you don't do greater than or equal to 0, you just do greater than, because we don't want to equal ever 0 in our denominator. So that's why we don't use the equal to. Everything else about this goes pretty much the same. So I would say I'm going to start at -3 and it's greater than, so we're going to be shading to the right. We need to throw out this other part of our denominator, which is just a rational piece. We need to throw out +3. So my domain goes from -3 to +3, and then from +3 to infinity. Because remember, greater than -3. Okay, so this portion, we're not really going to do much with that. We're just going to talk about it. Increasing, decreasing, and constant is just something that you would talk about again in calculus. If a function is going uphill, which means as the x's get bigger, the y's are also getting bigger, that means you have an increasing function. If your function goes downhill from left to right, in other words, as my x's get bigger, my y's get smaller, you have a decreasing function. As your x's get bigger, your y stays exactly the same, you have a constant function on that interval. So you can talk about increasing, decreasing, constant if your entire function does it, or you can talk about it on specific intervals. So what we're going to do with this is we're going to graph a couple of functions, sketching them, list their domain and range, and then we're going to talk about if they're increasing, decreasing, or constant. So, and you can graph these using any method we've used so far. So for this first one, for example, I'm going to do it by y equals mx plus b because it is a linear equation. So this is m and this is b. So just like we learned in our previous video, you plot the y-intercept first at +3. My slope is -2/1, so that would be down 2, right 1. And I'll do that a couple times to get a good picture of the graph. I could also go up to left 1. Oops, that is not lined up with that. On just a second. All right, let's try drawing that line again. Okay, so if it's a polynomial or a linear equation, it has a domain of all real numbers. Any x I want to plug in on the number line, I can, and still get a real number answer. The range, this also, if you look at the graph, it goes up and down forever. So it's also -infinity to infinity. And lines do only one type of increasing, decreasing, or constant. If it's a straight line, it's only going to be doing one of those. This is getting a downward slope, negative slope, so it's going to be a decreasing function on the entire interval of the domain. That is very important. Decreasing, increasing, and constant is always related to the piece of the domain that you're on. Okay, so there's my first one. Let's do this x squared one. So if you don't know how to graph a quadratic, which we haven't learned in detail yet, you can do a table of values. Typically, we pick things like -2, -1, 0, 1, and 2. Just plug them in and see what we get. We should know that it has a U shape if it's a parabola, because we learned that in section 3.1 or 3.2. So that is 4 minus 1, so that's going to be 3. -1 squared minus 1 is going to be 1 minus 1, so that's going to be 0. 0 squared minus 1 is 0 minus 1, which is -1. 1 squared minus 1 is 1 minus 1, 0. And if you've got your 5 points picked correctly, you should see some symmetry when you do a quadratic in the y values. So -2, +3, -1, 0, 0, -1, 1, 0, and 2, +3. There is the standard U shape of a parabola. Okay, it is still a polynomial, so its domain is any real number. But the range is restricted. Notice there is a lowest point on my graph. The lowest we ever get is -1, but we can go higher forever. So this keeps going up. This one has two different situations. You're downhill to the left of 0 because that's where this changes direction. And we're uphill to the right of 0 because remember it's the x value that determines the increasing, decreasing splits. So I am decreasing from -infinity to 0, and we don't include those. These are always parentheses because you can't increase or decrease at a single point. You have to have multiple points to compare. And I'm increasing from 0 to infinity, so I'm going uphill. So remember, this is in terms of our domain. Okay, we have just 2 more of these. So this is the square root of 4 minus x. I can use what I've learned about domain from previous parts of today to figure this out before I do a table. I know that 4 minus x has to be greater than or equal to 0. So I could either add the x over, which is what I'm going to do, or I could subtract 4 and then divide by -1. Remember, you can rewrite this if you swap everything, so swap the numbers and the inequality. So I already know my domain is going to be -infinity up to +4. But the reason I wanted to write that is it helps me pick my table. So I know I can only pick things that are smaller than 4 or equal to 4. So I am going to use 4 because that's my endpoint. And then I can pick 3, 2, 1, 0. May not use all of these. We'll just see which ones give us nice numbers. Square root of 4 minus 0 is square root of 4, so that's going to be 2. 4 minus, sorry, that was supposed to be 4 minus 4. I was doing the last guy first. Let me fix that. This was supposed to be 4 minus 4 for the first one. So 4 minus 4 is 0. Square root of 0 is 0. 4 minus 3 is 1. Square root of 1 is 1. I'm not going to do 4 minus 2 because that's square root of 2. That's a decimal. 4 minus 1 is square root of 3. That's also a decimal. I'm holding out for perfect squares. So square root of 4 is 2. So we have 4, 0, 3, 1, and 0, 2. So notice this looks like half of a parabola kind of on its side. So the domain we already had was -infinity up to 4. The range, the lowest my graph ever gets is 0. And it goes up forever. It's just going up very slow. This one is completely decreasing. So this is a downward hill the whole way from left to right. And it's only on its domain though. So this is decreasing from -infinity to 4. And we don't include that when we talk about the decreasing. Remember, we don't include a single point when talking about decreasing, increasing, or constant. All right, the final one. This is the equation just y equals 3. Remember, f of x is the same thing as y. So this is just a horizontal line at y equals 3. Not very interesting. The domain is still any real number because it is still a polynomial technically. The range, though, is a single value. So we put that in a set. So if your range is a single value, that's the only y value we ever use, it becomes a set of one number. And then this one is constant on its entire domain, which is from -infinity to infinity. Okay, there's only 2 things left in this video because this was the longer of the 2 sections today. So looking at the difference quotient. So we actually already did the difference quotient up above. We're just going to explain what it is now and give it a name, kind of. So it's a special interest in calculus to look at slopes of tangent lines. But because that's really hard to figure out the slope of a point of a line when you only know one point, what we actually do is we look at something called a secant line. A secant line crosses a curve twice. So you notice they've drawn 2 dots here. And then they named these points just very generically. They said this was A on the x-axis, and so that would be f of A. And they said this distance between these 2 points is h. So this would be the value, however much we went for A, plus an extra h that we added after it. So they're calling this A plus h. Okay, so it's the original distance plus the extra distance. And so that would have the y point of f of A plus h. And what they say is, if you do the slope formula with this, f of A plus h, I'll write that down. So we're just doing slope formula with P and Q. So the slope of PQ would be, write this a little smaller, f of A plus h minus the f of A, because that's the y values, over A plus h, which is this x value, minus A. And what you'll notice is the A and the negative A in the bottom cancel out. And that gives us the formula we were looking at earlier, and it has this name called the difference quotient. So so I had this written here, but I wanted to show you the A minus A part. So The big thing here is that in calculus, you do something called a limit. You watch as I shrink the distance between the 2 points to nothing, essentially, to make it a single point. And that's kind of where they get the slope of the tangent line. But again, you're not in calculus, so you don't have to know to do that. We just want to evaluate the difference quotient. They won't always use A in the formula. Sometimes they'll use X. So notice this is the same formula, but they use X plus H and X instead of A plus H and A. Same idea, just different letters. So we're going to use this to evaluate the two functions on top. That's how I usually approach it. And then we're going to put it into our fraction and put it over H and reduce it. So the first thing I want to do is find the X plus H. So that's -2 times X plus H squared plus 3. I write my X plus H twice. I FOIL it out. So that's going to be X squared plus XH is 2XH's plus H squared. Distribute that -2 into your parentheses. It does not go to the 3 because the 3 was not in the parentheses. Then we're going to do negative f of x because that's the second evaluation, just like we practiced earlier. That is -1 times your function. So that's positive 2x squared minus 3. So remember, just like before, we put those into my difference quotient formula for my numerator. So the first one is the -2x squared minus 4xh minus 2h squared plus 3 plus 2x squared minus 3, because that's my negative f of x, all over h. If you've done it correctly, everything that does not have an h on top in these polynomial ones will cancel out. And we get -4xh minus 2h squared over h. And canceling out and reducing an h from each term gives me -4x minus 2h. Now, in calculus, where they would go with this is they would say, now let h approach 0, which means you would zero it out, and you would have -4x. And that's actually something called a derivative. And that's, like I said, you're like 2 steps away from being able to use calculus in a certain way by knowing how to do this evaluation. So for us, all we want to be able to do is to write the final answer after reducing the h part. Okay, the final thing in this video is linear functions. So only thing different between y equals mx plus b and this is you're calling it a function. You're saying f of x. So again, if I have 2 ordered pairs and I can write the slope and then I can do point slope to find the equation, then I can get the function. So that's all we're going to be doing for this one, because technically they have given you 2 ordered pairs. They told you the x that they plugged in and the y that came out. So this is the ordered pair -2, 7. This is the ordered pair 4, -2. If we find the slope of that, that's -2 minus 7 over 4 minus -2. So that's going to be plus plus. That's -9 over 6. So that reduces to -3/2. You can use either one of the points you want. It doesn't matter, but I'm going to use my point and my slope. Write it in point slope, just like in section 3.31. This would be y minus 7 equals -3/2. X minus a -2 would be plus 2. And you could technically distribute this if you want. I like to multiply both sides by the denominator and get rid of the fraction. So I'm going to multiply both sides by 2. So this would be 2y minus 14 equals, that's going to be just -3 to distribute. So that's going to be -3x minus 6. Add the 14 over. It's going to be positive 8. Divide everything by 2. And then we write it as a function because they did say write f of x. So f of x for this specific set of ordered pairs is f of x equals -3/2 x plus 4. All right, so that's everything that you guys need for the missing class on Thursday. So make sure you've watched 3.3 and 3.4, both pre-videos, and do your pre-work, and then obviously the in-class notes that we just finished. And I will see you guys on Tuesday of the next week. Don't forget, we do still have class tomorrow on the 10th.